All right, everybody. This is going to be a balancing redox and identifying redox agents and that sort of thing. This is from the balancing equations using redox methods in your booklet, page 21. So we'll start with this copper and aluminum one. This one's a little bit more straightforward. So the very first thing we want to do is identify our oxidation states. So I'm going to look at my aluminum. It's a metal. It's all by itself, so it's a pure element. The oxidation state is 0. The other pure element is the copper on the other side, so that one's also 0. And now it's just a matter of identifying these other ones. We have some options here. We see that these are sulfates. So if we go to our sulfate table, or our table of polyatomic ions, we'll find that sulfate as an ion has a 2- charge. So we could treat this all as one thing and say that this is 2-, and that means that the copper must be 2+, or in this case, it's kind of fictional charge. So +2. Over here we have, if we apply the same logic, we have a -2, but there are 3 of them. And there are 2 aluminums. This is getting a little tricky, so I'm going to do some math down here. So I'm going to go 3 times -2 to get -6 down here. And I'm going to think, okay, for my aluminum, I'm going to need a +6. And I've got 2 of those, so I'm going to divide that by 2 so that each aluminum is +3. In fact, in some of the oxidation rules, you'll find that aluminum is often given always a +3. So you can sometimes just make the assumption that it's +3.
So how do you get it? Like, oxygen is -2, so multiplied by the coefficient is 3, right?
Correct, yeah. So we are taking the -2 multiplied by the subscript there of 3, which is showing that there are 3 of those sulfate units. Each sulfate unit is a -2, so 3 of them gives us a -6. So that's the concept there. I ignored the 4 because I treated the sulfate all as one big unit. Okay, so I'm going to do a little bit of cleanup here because that makes my life a little easier to look at. So I'm just going to clean this up, and we have a record of it. Notice I don't really care about these sulfates because it's a sulfate on the left and a sulfate on the right. So it's not the sulfate that changes. If the number of oxygens had changed, then I got to get worried. But because there's no change in the number of oxygens, we can treat this whole thing as a unit, as a little ionic unit, and that ionic unit didn't change oxidation states. There's no change in that unit. So now I'm just looking at the aluminums and the coppers. I probably could have made a guess that it was aluminum and copper since those are the 2 metals on the left and right. So my aluminum goes from an aluminum 0 to aluminum 3+, and my copper goes from a copper 2+ to a copper 0. So the aluminum oxidation number is increasing, so that means that that is the oxidation. The aluminum is being oxidized. So when the number increases, that's oxidation. When the number goes down, reduction. I sometimes go with the down first because down and reduce makes sense, it fits together.
Or if there is a way, like a zero integer, like from negative to 0 positive.
Yes.
So if it is from negative, it goes to the positive one, it's an oxidation. If from the positive goes to the negative, which means it's
So the suggestion is the idea that if you think about it going this way,
exactly.
then going this direction is reduction, and going this direction is oxidation. So I'm going to identify my aluminum as being oxidized. I'm going to actually say that each aluminum is losing 3 electrons. So the aluminum is changing into aluminum 3, or +3. And that means that it's producing 3 electrons on the left. So the electrons have to be ripped off the aluminum. That's how that aluminum is becoming oxidized. On the other side, I have a copper 2 plus, and that copper 2 plus, or I know I should be better at writing these, plus 2, is getting 2 electrons to form a copper metal. And so this is going to be a little bit of a finer pen here. This one is reduction. And this one down here is oxidation. So we can say that aluminum is reduced, or is oxidized, sorry, is oxidized by the oxidizing agent. The agent, this is the person that is responsible for this, or person, the chemical. And so the chemical that causes this aluminum to be oxidized would be the copper sulfate. That's the chemical, right? So that's what I would grab off my shelf. I can't actually just grab copper ions off my shelf. Those aren't available on my shelf. By the same sort of turn of phrase, we could say that the copper is reduced by the reducing agent. And in this case, the reducing agent is just plain old aluminum. This could probably just be some aluminum foil even. If you just took some aluminum foil, dropped it in solution with some copper sulfate, you might actually see some copper metal forming. So that's the idea here. Now, we know from a later unit that we'd actually have to go in and do a little bit of calculations to see if it's even going to happen spontaneously, but we'll assume that it does.
How about the 2 in aluminum?
Right, so now it's time to do the balancing act, right? So I'm going to write out my half reactions before I start balancing. So I just wanted to make sure we had a complete story here. So aluminum goes to aluminum, 3 plus 3 plus 3 electrons. I just want to think about this just 1 second. So each aluminum gets 3 electrons, and each copper requires 2 electrons, right? I know what I mean. I know what I want to do. I want to try a different way. Okay. So each aluminum releases 3 electrons per aluminum. Right. We did this. Okay. I think I'm actually happy with what I was doing before. I'm gonna go back. Okay. I'm gonna keep going with this. I'm gonna take these half reactions. I'm gonna keep working on those. Okay. Give us copper. We can notice that we can then think about balancing this reaction, right? So I have 3 electrons being released, and I have 2 electrons being absorbed. So I need to make sure that I have a balance there. 6 electrons would be a very good balance. So that would be 2 aluminums and 3 coppers. And the good news is that copper sulfate is not a it doesn't have more than 1 copper per unit. So I can actually pretty easily kind of go in here and do a little bit of editing, get rid of this, and put an SO4. And I've made copper sulfate. Didn't have to change anything. And I do have to finish some multiplication. If I have 3 of those, then I'm going to also do sort of 3 times this to give me 6 electrons. I'm going to produce 3 coppers. If I did 2 aluminums, then I'm going to produce 2 aluminum 3 pluses, and I'm going to change this to 6 electrons. All right, so that looks pretty good. I'm gonna be worried about this here because I noticed that in my that I have something a little strange in my structure there. So what we can do is we can focus on the reactants first. So these two reactants are solid. Those ones have to be in that ratio. So I'm going to put that in my equation. 2 aluminums plus 3 copper SO4. And that has to produce an Al2 SO4 3 plus copper. And then I'll balance my reactants now that it's I will balance my products now based on the numbers I have. So 2 aluminums, that's balanced. I have 3 coppers, so I'm going to put a 3 here for copper. And then I have 3 times sulfate and 3 times sulfate. So that is the balance there. Got a little messy at the end there, but there's be a couple other ways you could do it. You could also have changed this to the Al2SO4 right away, and then just combine the two reactions. That would also work out in my favor. This is just essentially that same idea of doing net reactions like we did in the ionic stuff. Very, very similar. Okay, should we do one more? We're good on that? Okay, so we'll leave it there, and if you have any other questions, let me know. Okay, so that's the first video there. I'll make sure that's, get back to my account here, to my channel. It should show up somewhere. Be on my live videos. Redox stream. Oh, yeah, it's up there. Okay, great. I'm gonna add that to a view on YouTube. Alright, ready? This is going to be a... There, it has sound this time. Goes from a copper... okay, so that's up. I'll put that on the... Save it to our electrochemistry one, which I will have to go and delete those other 2 videos, which are not useful. Okay, so what's the next concept we should go?
Lesson 4.
Lesson 4. Okay, redox activity series. Okay, so as I said, I sort of kind of skipped through this a little bit because we got straight into the using the potentials to do the same calculations. So that's where because I really don't like this spontaneity rule that the reactions are upright. That doesn't make any sense. That only applies if you have the right table, right? So maybe we could explain some of this stuff. So that's why I made that separate video that kind of got into that. All right, so let's see if we could do this. How could we do this?
So it is just like a spontaneous reaction and a non-spontaneous reaction.
That's what we need explained?
It is spontaneous. If it is an aldehyde, it is not spontaneous.
Yes. So the idea is so they're saying that we can make, if it's as long as our reactants are formed from something that's a better oxidizing agent than the metal we're reacting with, then that's the direction the reaction will go.
So the direction should go from left to right.
Yes, from bottom left to top right on the series. If you have the series organized in that direction, right? So sometimes you pull up a table and it's upside down, and then that's not very useful. So that's why I kind of jumped that lesson. And it doesn't really, unfortunately, we don't really get back to it fast enough until we get even like farther down, like. So let's just write let's do a little new video, maybe let's do the activity series. I'll do these activity series questions here, but I'll do it with with that, with the, I know, okay. I'll do a reduction potential table.
Did you send the new one? But this one is it wasn't complete.
Yeah, so we'll pick a, I just need a table here and then we can get going on this. Something like that. Standard reduction potentials. This one's okay. How about